Alright, so now we're going to look at curvature. In this video, we'll just look at the definition, some examples, and real basic properties. Well, somewhat basic properties, and then in a future video, we can get into another formula for calculating it. So, first I wanted to recall, we have our smooth curve that we're dealing with up here. We have, it's parameterized by r of t, and the domain for the parameter is a to b. Okay, then of course we have our unit tangent, our unit normal, and our unit binormal, defined as before. They are mutually perpendicular unit vectors, right? They're all length 1, perpendicular to each other. And then another thing worth mentioning is that they form a right-handed system. We have t cross n gives us b, n cross b gives us t, b cross t gives us n. So they behave a lot like I, j, and k, the standard unit vectors. All right, remember that t kind of tells us forward, n to the left, and b is thought of like up, just like you can think of I, j, and k. The next thing we want to remind ourselves of is the arc length function. Remember that if you integrate from the beginning of your parameterization a to t, you take the integral of the length of the derivative of your parameterization. That gives you the arc length function. It begins at 0 and it goes all the way up to the total arc length of the function. And then another property worth pointing out about the arc length function that will show up at various times is that the derivative of the arc length function by the fundamental theorem of calculus would be the formula inside that integral with the dummy variable replaced by t. So let me try that again. All right. So we have the derivative ds of s, ds dt is length of r prime of t. Alright, so now we're ready to define what we mean by curvature. So curvature is nothing more than the rate of change of the unit tangent vector's length, except we're going to look at the rate of change with respect to arc length. Remember that if we reparameterize our smooth curve with respect to arc length, we end up with a standard parameterization where we move along the curve at unit speed, and that's a built-in parameterization. It's something built into the curve that's determined by the shape of the curve. And so curvature being defined by looking at a unit tangent, the unit tangent is determined not by the parameterization but by the shape of the curve and its orientation, and then the arc length parameter, again, that's determined by the shape of the curve. And so this rate of change is something that has something to do with the shape of the curve, not the particular parameterization we have. It's independent of the parameterization used. By the way, we denote curvature with the Greek letter lowercase kappa. It looks like a k, but just as a notational note. Now, let's go ahead and look at how would we go ahead and define and compute curvature. Remember that reparameterizing with respect to arc length is totally impractical in general, so we want a way to get a formula that doesn't involve that kind of reparameterization. So what we do is we turn to the chain rule. So remember that dTds, this could be rewritten as dTdt times dTds. That would be the derivative of the inverse of the arc length function. Remember, the arc length function's increasing, so it's invertible. This would be the same thing as taking dt and dividing by, well, it'd be ds dt, right? So we know that's the way derivatives work. The derivative of the inverse function is reciprocal of the derivative of the function. And so now we can look at this and go, well, you know what? If we want to find the rate of change of dt with respect to arc length and look at its magnitude, that's nothing more than the magnitude of the rate of change of t with respect to t, the derivative of t with respect to t, so we'll just call that t prime. And then down below, ds dt, we should recognize that from before, that the derivative of the arc length function we know happens to be nothing more than the length of r prime of t. So we get this rather nice simple formula for kappa that does not involve reparameterization with respect to arc length. So kappa can be computed as the length of t prime divided by the length of r prime. As a quick example, let's refer back to the helix that we found the TNB frame for in a previous video. So we have 3 cosine t, 3 sine t, 4t. And I'm going to recall from that video that the length of r prime of t turned out to be 5, and the length of t prime of t turned out to be 3/5. Okay, that was calculated before, or it'd be easy enough to redo that calculation. So if we've computed the TNB frame, we've computed these values along the way, and I can now put that together and get quite easily that kappa, the curvature for this helix, is length of t prime divided by the length of r prime. In other words, it's 3/5 divided by 5, or in other words, 3/25. Okay. Let me point out that curvature kappa isn't usually constant, right? It's usually a function depending on t or whatever your parameter is. But for a helix, any kind of circular helix, we're always going to have constant curvature. And if you believe that curvature is some sort of measurement of how a curve is bent, then that should make pretty good sense, because a circular helix is kind of bent in the same way at every point on that curve. All right, let's look at 2 important examples of curvature. I'm going to go ahead and clear our page. I want to look at, first of all, the example of a circle. Okay, so let's go ahead and do this in general. We'll have a circle in general, in 2 space anyway, has this kind of equation. This, we're thinking of r as a fixed positive constant, a and b being some fixed real numbers. And of course, we can parameterize our circle. We have a standard parameterization, which falls out from polar coordinates, really. That circle is r cosine of t plus a, being the x coordinate of the center, and r sine t plus b, b being the y coordinate of the center, and t goes from 0 to 2 pi. And so I want to go ahead and compute curvature, so let's go ahead and compute the derivative of r. That's minus r sine t, r cosine t. Notice that we can pull an r out of that. And next thing, we'll compute its length. Well, that just happens to be r. Remember that as we take the length of minus sine cosine, we'll end up with sine squared plus cosine squared, square rooted, and that's just square root of 1 is 1. Okay, putting this together, we have that the unit tangent, that's just the derivative normalized, that happens to be 1 over r times r minus sine cosine. So that's, you notice that r's cancel off, so our unit tangent is just negative sine cosine. Well, we can take its derivative. This would be minus cosine minus sine, and that has length 1. It's already a unit vector, so in fact, I'll just say secretly that's the same thing as n, although we don't really need to know that. And so putting this together, we have that kappa is the length of t prime over the length of r prime, and this is 1 over r. Now let's reflect on that for a little bit. The curvature of a circle is the reciprocal of its radius. Does this make sense geometrically? And I would hope, if you think about it for a while, that this would make great sense, right? Which is more curved, a small circle or a big circle? Obviously, the smaller the circle, the more it's curved. In fact, as we draw, get this to behave itself, if we draw successively bigger and bigger and bigger circles, eventually circles start to look like very much like a straight line. And so the larger the radius, the less curved our circle is. The smaller the radius, the more curved our circle is. So curvature and the radius should have a reciprocal relationship. Okay, let's consider another basic example, and that being a line. Okay, so we know that we can parameterize lines, get it so that we have a point and then a direction vector times time. And so if we go ahead and compute the derivative of our line, well, p is a constant, v is a constant, the derivative of t is 1, so we just end up with v. And if we take the length of r prime, that's just the length of v, our kind of the direction for our line. Okay, and then that means the unit tangent is just v normalized, which looks fancy, but that's just a constant vector, right? Which makes sense, right? A line has the same tangent direction no matter where you are on it. Okay, and now we take the derivative of the unit tangent and we get 0 because the derivative constant is 0. And so what is kappa? Kappa is the length of t prime over the length of r prime. This is just 0 over the length of v, which on a good day is 0. We just found out the shocking fact that lines aren't curved. What do you know? Okay, and that makes sense. In fact, the converse is also true. If kappa is 0, we must have that that this guy is 0, which would say that the unit tangent's derivative length is 0, which would say that the unit tangent's derivative is the 0 vector, which says that the unit tangent itself is a constant. Well, so what this would then mean is that if we pick a unit speed parameterization, this would also be the same thing as r prime. And so what we would have to have then is that for a unit speed parameterization, r is just this constant times t plus some other arbitrary constant. In other words, we have a line. So we have that lines have curvature 0, and if we have curvature is identically 0, we must have a line. And that kind of goes to show that lines are basically like circles with infinite radius. Okay, and that should kind of make sense, right? The bigger, as you pick a bigger and bigger and bigger circle, your bigger and bigger and bigger circle starts to very much look like a straight line. And so if you took a circle as its radius approaches infinity, you end up with 0 curvature, which is nothing more than a line. Okay. Oops. Let's clear this page. Okay, so now let's look at a few other quick properties of curvature. And we have a couple examples in hand. First of all, I want to note that n is t prime normalized, of course. And if we stare at that for a little bit, we'll notice that, well, you know what, this is t prime, and we could, I don't know, let's multiply and divide the bottom by the length of r prime. Okay. If you do that, notice that's t prime divided by the length of r prime times kappa. Okay, so in other words, the derivative of the unit tangent is kappa times the length of r prime times n. So if we use, if we reparameterize with respect to arc length, so we take a unit speed curve, well then we would have that dt ds, I'll write it the derivative that way to emphasize we're differentiating with respect to s, would be kappa of s, and in that case the length of r prime, we have r prime of s is ds ds, that's just 1, it's a unit speed curve, so that doesn't have to show up in our formula, and we end up with the cleaner looking result that the derivative of the unit tangent is curvature times the unit normal. But again, in general, it needs a little adjustment to figure in the speed of our curve. Okay, so that's a nice relationship to keep in mind. Another thing we want to mention is osculating planes and circles. So if we take a curve, at any particular point on that curve, right, we have a tangent, a normal, and a binormal. Well, as long as our curve is nicely behaved enough, right? If we have a smooth curve and its curvature isn't 0, if we don't have that the length of the unit tangent's derivative is 0, we can compute Tn and B. I maybe should mention that, if you go back to look at the calculation for a line, because t prime is 0, you couldn't normalize that. So lines don't really have a well-defined unit normal, and thus also not a binormal. But usually we'll have things that are curved, and we'll have a well-defined T and B frame. And let's take a moment to point out that we have names for various things. First of all, if you take the plane, this guy is parallel to T and N, and perpendicular to B. Okay, so if we wanted a vector equation for this plane, at a particular point on our curve, B would be a normal vector for that plane, and we would have x, y, z minus, and then r of t naught would be that point on the curve. So this is a vector equation for such a plane, and that plane right there is called the osculating plane at that particular point on the curve. To osculate is to kiss. It's a kissing plane. This is also called it's called the osculating plane. There's a couple other planes that we might mention. I don't think come up quite as often in what we want to do, but the plane spanned by that's parallel to N and B, so this would be perpendicular to T, is called the normal plane. Okay, so the normal plane, you can think that your curve kind of, the normal plane like chops right through your curve, right? The T points forward and this plane just kind of chops right through it. And then there's another plane spanned by T and B, so if we're parallel to T and B, in other words perpendicular to N, that plane is called the rectifying plane. Okay, so associated with T and B at a particular point on the curve, we have three planes, osculating, normal, and rectifying planes. Of those, really the most interesting one is the osculating plane. Let me go ahead and point out, if you go to my Maple example page, you can find under multivariable calculus, there's let's see, let's go to arc length, curvature, and T and B frames and give you an example here. So for this ellipse, that plane drawn in yellow there is the osculating plane. It perfectly matches our curve at the point that we're basing this at. If you scroll down, let's see if we can find another example. Okay, right here, at that red dot there on the helix, that's the osculating plane. And what you can see is that the osculating plane is perfectly approximates what plane that curve sits in as it can. Now, of course, this helix doesn't actually sit in a plane, so it twists out of that. But at the red dot there, right at that single point, it very nearly is a planar curve. And so the osculating plane kind of kisses the curve at that point, and that's kind of its function. Want to mention in relation to the osculating plane, we have an oscillating circle. So right, this is also called a circle of curvature. And what this does, it's basically like a tangent circle. So a tangent line best approximates your curve with the best line that you can come up with at a particular point. This oscillating circle does the same kind of thing with a circle. So let's say that, let me try that again. Let's draw just some random curve. Okay, and then at a particular point, what I'm going to do is, let's say here's our T, and then we have, here's our Rn, perpendicular to that, and so this curve right at that point's lying in the osculating plane spanned by those two guys. And what we're going to do is draw a big old circle based at that point. And so the center of our circle, the center of that circle, what we're going to want to do is have the center be, we're going to start off at the point on our curve, r of t naught. Then what I want to do is I want to move in the unit normal direction. And so I actually want to move that, how far do I want to move out? I'm going to move 1 over kappa of t sub naught units out. So I'm assuming curvature isn't 0. That's what that center is. And then I want to take and create a circle of radius 1 over kappa. So I'm going to take 1 over kappa times cosine of t, and I want to have 1 over kappa times sine of t, 1 over kappa t naught sine t, and 1 over kappa cosine t. And I'm going to use cosine to scale t. I'm treating it like it's the I vector, and I'm going to take sine and scale n. So this is t of t naught, that's n. Let me try this again so we can better see. Oops. Okay, so we'll have 1 over kappa of t naught, cosine of t, t of t naught, and again, think of that kind of like it's an I vector, and then we have 1 over kappa of t naught, sine of t, n of t naught. Oh well. Okay, and you think of n as kind of like a j vector. So if you remember the way we parameterize a circle, you have r cosine and r sine. So what we're doing is we're creating a circle of radius 1 over kappa. Remember, first, the curvature of such a circle would be 1 over its radius. It would have if the radius is 1 over kappa, the curvature of that circle is kappa, and then we're just putting the center at appropriate point. So what we get is the osculating circle lies in the osculating plane at whatever point where we're working, and its curvature matches the curvature of our curve, and so it will give the best circular approximation of our curve we can hope for. And again, if you go back to my maple page, you can see lots of examples of this to get an idea of what the circle of curvature is, the osculating circle. In fact, if you go all the way to the, well, let's go back to my main example page. Come on. What I have here, up at the top of this animation, that gray circle is actually an osculating circle. If you scroll down, you can see I have in arc length curvature and T and B frames, there's lots of examples here where I've drawn in osculating circles. So on the yellow plane there's a little blue circle, that's an osculating circle. Let's see, right here, this weird blue curve, that green circle is the osculating circle at a particular point. Anyway, if you scroll through, there's lots and lots of examples. There's a osculating circle for that helix. And better than that, if we go back to my maple example page and look under osculating circles just below arc length curvature and T and B frames, I actually have example of computing oscillating circles at various points along, say this is a sine wave, and you can see the line there is a normal line. It's perpendicular to a tangent line. And then there's just the osculating circle being plotted for various points along the circle. Here's osculating circle and the normal line along a parabola. And you can see again, the more the curve is bent, the smaller the circle. The less the curve is bent, the more the osculating circle starts to look like a straight line. Notice at inflection points on this bell curve here that the osculating circle becomes basically a straight line again, and that at that point the curvature at those inflection points is 0, and the osculating circle really isn't actually well defined there. In fact, it should be replaced by the tangent line. Okay, so hopefully spend some time exploring those and getting yourself a good feel for what we mean by an osculating circle and what curvature really says.